Okay, so here we have section 6.4, and this is about finding the volume of functions by using the shell method. So what we're going to have to do is, here is a picture of what the shell looks like, and we have the choice to rotate around the y-axis or the x-axis, so it's going to make a difference what we do. And since we're going to end up having a circular portion, we're going to end up talking about the circumference, okay? So the circumference is going to be represented by 2 pi x, and whatever the x value is going to be the radius. So this is going to be the radius. And then the second portion here is going to be the height of the shell. Okay? Okay, so let's go ahead and dig into an example. Okay, so here we have, we are trying to find the volume of the region bounded by the function f of x, which is sine x squared, and the x-axis, and the vertical line shown at x equals square root of pi over 2. And we're rotating around the y-axis, so we're rotating around here, okay? All right, so the first thing that I want to draw your attention to is that our interval of integration is going to be from 0 to the square root of pi over 2, and that's because that's the bound that they gave me. So land equals. Okay. And then in this case, our radius is the distance x, okay? And our height is our function represented by this line here, which in this case is sine x squared, okay? So we're going to say 2 pi x, and we have sine x squared minus sine of 0. All right, sine of 0 because that's the lowest that our x value goes, okay? All right, so let's just clean this up just a little bit before we do anything else. Okay, so sine of 0 is just 0, so that can go away. Don't forget to write dx. Okay, so now if I were going to integrate this, I would actually have to do u substitution. So what we could do is we could say that u is equal to x squared. Therefore, the derivative of u would be 2x dx. So now I need to see what of this that I have. And I have the 2, and I have the x, and I have dx. Okay, so that's good. So that means I could just write that as sine u du. Okay, so remember, when we're doing u substitution and we have values that we're using for our integration, we need to make sure that these numbers are correct with what we said that u is equal to. So in this case, since u is equal to x squared, what I need to do is I need to plug in 0 squared, which is just 0, so that's going to stay the same. And then I also need to plug in the square root of pi over 2 squared, which is just going to give me pi over 2. Okay, so then if I rewrite that, my new values that I'm going to evaluate are 0 and pi over 2. I still have pi, and I'm integrating sine u. Okay, so what does the integration of sine come from? or what gives you sign for your derivative? And the answer is cosine, but not just regular cosine. I need the negative. So I'm going to end up with negative pi cosine u. And I'm going to plug in pi over 2 and 0. So that's going to give me negative pi times cosine of pi over 2 minus cosine of 0. And I'll get negative pi, 0 minus 1, which is going to give me negative pi times negative 1, which is pi. Yay. Okay. Let's do a couple more examples. These definitely are a little weird. And they take practice. Okay. So I know we're winding up the end of the year. And this is our last section that we're going to talk about. So yay. Okay. So in this case, we're working with the first quadrant. Okay. So I only care about the values in the first quadrant. Okay. So let's draw a picture. What do we have going on? We have the region bounded by the graph of this y, so the square root of x minus 2, and the line y equals 2. Okay, so y equals 2 is here. And if I graph this, it's going to be something like this. Okay, this is 2, 0. So we're talking about this area here. Okay, and we are going around the x-axis, so it's like spinning like this. Okay. Okay, so then the other thing that I'm noticing is I can see where these two lines intersect. And I can do this in Desmos, or I could also solve and set 2 in for here. So if I do that, I would get the answer of 6, 2. Okay. Okay, so let's work this out. So we need to know what the radius is, and in this case, the radius is going to be 2, or y. Okay, so the radius is going to be y because the radius here is 2, but the radius here is going to be whatever the distance is. Okay, so our radius is going to be y. Okay, since we're going around the x-axis this time, we are looking at the y to see where we're integrating. So our interval of integration is going to be from 0 to 2. Okay, so that's from 0 to 2. And we're going to have 2 pi y. That's part for my radius. Okay, so now we need to figure out this next part. So to figure out the height is dependent on here, which is dependent on my function, right? So what we're going to do is we are going to solve our function for x. So the first thing I'm going to do is I'm going to square, and then I'm going to add 2. Okay. All right, so this is telling me that my height is going to be y squared plus 2. Okay. Okay, so all right, and then this one is nice in the sense that we are going around the x-axis, so there's not going to be any gap here. So essentially, I don't have another piece to my formula because in this case, the lower bound is just going to be 0. Okay, so it's my function minus the other piece, and in this case, the other piece is 0. So I'm still going to write it just so that we have that as a reference, but we don't actually need it. Okay, so now let's take out the 2 pi so we don't have to worry about that with integrating. And then we're also going to distribute in the y. So we're going to end up with y cubed plus 2y. Now we can easily perform the integration. And I'm going to evaluate that at 2, 0. And if I do that, I'm going to end up with 16 pi. Okay, so this next example is really, really similar, except for the next example, we are now going to be rotating around the line y equals -2, okay? So this is going to look like a really similar picture to what I drew on the last example. Okay, so as this is rotating around here, you're going to end up with this kind of hole in the center, right? If I was more skilled at drawing, I would try to draw it, but there's probably a really nice picture in your book that you could reference. Okay, so in this case, because this gap is happening here, my radius is now going to be y, whatever the y value is, plus 2. Okay. My height is still going to be y squared plus 2. Okay, so let's go ahead and plug this in. My integration is still going to happen from 0 to 2. Okay. All right, so first we're going to take out the 2 pi so we don't have to worry about that when we integrate, and I'm going to go ahead and FOIL this out. All right, and let's integrate now. And we're going to evaluate that on the interval of 2 to 0. So if we do that, we're going to end up with 128 pi over 3. Okay. Okay, so we have something else that we're going to talk about, and so we've talked about the disk and washer method, and we've talked about the shell method. Okay, so this is just a summary of the disk and washer method versus the shell method, and then the next thing is the same but with respect to y now. Okay, so let's go ahead and complete the next problem. And this is actually going to be the last problem that we're going to do. So in this case, we're going to use the washer method to find the volume of the solid formed around the x-axis, okay? So this is like what we were doing in section 6.3, okay? Okay, so we have g of x, and we have 2x minus x squared, which looks like this. Okay, so you can either set these equal to each other, or you can plop this into Desmos so you can see that they're intersecting at 0, 0 and 1, 1. Okay, so in this case, we're using the washer method. And for the washer method, the rule is you're going to do, so my integration is from 0 to 1, and it's pi multiplied by your first function, the upper function squared, and we're going around the x-axis, so we're going around here, minus your second function squared. Okay. All right, so let's clean this up a little bit before we integrate. How many times have I said that? Okay. And combine like terms. So we're going to get x to the 4th minus 4x cubed plus 3x squared. Okay, now we can integrate. Okay, let's go ahead and evaluate. And if I do that, I'm going to get pi over 5. Okay, so we were using the washer method. So essentially what we did was we spun this guy around, and then we calculated their volume, right? Okay, so now looking at the same exact example, but this is using the shell method. Okay, so same problem, different technique. Okay, so in this case, we need to first solve this equation for x, okay? Because this one's easy. It's just x equals y, okay? So now let's do the other one. All right, so this is going to end up being this. Okay, so what we would need to do, let's see, 2x squared minus x equals y. It's going to be yucky. So just trust me, because you're not going to have to worry about this, because I'm going to show you something in a second. You're going to be like, what? Okay, so in this case, when we're doing the shell method, we're still evaluating the integral on the bounds of 0 to 1. And our radius in this case is just y. Okay. And the height is going to be y minus this whole thing. 1 minus square root of 1 minus y. Now you're probably already getting a little bit frustrated because you're like, this is a lot, right? So we would need to integrate this. And I mean, besides like me writing it like this, just getting rid of the negatives, this would still be kind of a really big pain in the butt to integrate. Okay, so the moral of the story is sometimes the washer method is going to work better and sometimes the shell method is going to work better. Okay, so on your final exam, what I've done is I've given you the way that I want you to do it to try to like minimize any confusion. But just know that when you encounter different problems in your calculus career, there's different ways to do them, and some of the different ways to do them would maybe be easier depending on the type of problem. Actually, just like, okay.